So thank you all for coming to our fourth workshop via Zoom. And today we'll be looking at calculations to figure out cell potential. So we're still looking at Ecell. We'll also try to calculate delta G and K. So these are three different values that we can calculate. So let's start off by just looking at an equation that kind of puts this all together. So we previously said that our Ecell, right, was equal to the difference between our cathode and anode reduction potentials. So if we said that for our standard Ecell, E naught of our cathode minus E naught of our anode gave us our cell potential, or our Ecell. So that's for our standard cell potential, and this is under standard conditions. So when we use the degree sign, this lets us know that we're talking about standard conditions. And for our standard conditions, we're defining this as all species having a concentration of 1 molarity, right? We're at 1 atmosphere of pressure, and then we're also at 25 degrees Celsius, right? So all of those requirements need to be fulfilled for us to say that we are in standard conditions. That's the only time that we'll use the degree sign. 1 molar of each species at 1 atmosphere at 25 degrees Celsius means we're in standard condition. So when we think about this new value, delta G, we're going to call this Gibbs energy. We're going to be introduced to a new formula that allows us to calculate the amount of energy in a reaction. So this is a different type of energy in a reaction. We'll call this delta G standard. And this is based off of, or one way we can calculate it is using our cell potential. So we'll take the negative value of the number of electrons in our molar ratio, and then we'll multiply it by Faraday's constant, which is just an electronic value that's calculated. And that gets multiplied by E naught of our cell, right? So we're talking about a standard Gibbs energy here. So since we're talking about a standard Gibbs energy, we need to use a standard cell potential. So now let's look at our first example, example 1, and see if we can work through a calculation to get a kind of a grip of this formula of this concept. So we're looking at the reaction where we have tin 2 going to tin 2 plus mercury going to tin 4 plus mercury liquid. And we're given the cell potentials, the reduction potentials for each half reaction. So the reduction potentials we're given are the half reaction for, so if we were to write out our half reactions, we have tin 2 going to tin 4, and we have mercury, Hg2, plus 2 going to 2 equivalents of mercury. And then we want to include our phase symbol, so mercury should be a liquid there, aqueous here. And then both of our tin species are aqueous. And then the last thing we want to do is make sure that we're balancing our charges by balancing electrons. So since we have a net change in charge of 2 for our tin, we should have 2 electrons on the product side. And then for mercury, since we have to add 2 electrons to get a neutral mercury liquid species, we need to have 2 electrons on the reactant side here. So by putting in our electrons, this automatically tells us which side is our oxidation and reduction half reaction, right? We can also use the oxidation numbers to figure that out, right? If our number is being reduced, then that's a reduction. If the number is being increased, then it's oxidation. We can also think of oxidation as electrons as our products and reduction as electrons as reactants. So that must mean that our reduction half reaction is our half reaction with mercury, and our oxidation half reaction is our half reaction with tin, right? So we have tin and we have mercury. And now what we want to do, since we know the half reaction for each, and we're given the reduction potential for each half reaction in the reduction direction, then what we want to do is we want to make sure that when we calculate E naught cell, so when we calculate E naught cell, we want to make sure that we're taking the E naught of our cathode minus the E naught of our anode. So we know that our oxidation occurs at our anode, and reduction occurs at our cathode. So with that information in mind, we can just combine our reduction potentials in the correct way in order to determine what those values should be, right? What our overall Ecell should be. So when we look at our reduction potential, we see that for the direction that we've written our reaction in, it's actually the reverse of the reduction potential given. So the reduction potential given is going from tin 4 to tin 2, but in our oxidation reaction, we're going from tin 2 to tin 4. So that means that we need to actually either, we can use this number as is or invert our value. So I'm going to do both methods. The first method I'm going to use is just the reduction potentials pulled directly from our equation, the redox potential table. So if I do that, then what I would get in my calculation is I would get the value of 0.8, 0 volts, that's the cathode reduction potential, and I'll subtract my anode reduction potential of 0.1554 volts, and this gives me an E0 cell of 0.646 volts. So that's one way we can do it when I take my reduction potentials directly from my table, reduction potential table. Another way that I can do it is I can actually calculate, right, the oxidation cell potential for my anode. And so for my oxidation cell potential, right, I'll take my reduction cell potential and take the negative value of it. So since I have, for tin, my reduction cell potential is 0.154. My oxidation cell potential should be negative 0.154 volts, 54 volts. And this is for the tin oxidation. And if I want to add oxidation, so if I want to use E0 for my oxidation, if I calculate Ecell, now I can add my reduction plus oxidation cell potentials to get Ecell. So now I would take my 0.80 volts and add negative 0.154 volts, and this gives me the same value, 0.646 volts. So my Ecell for both of these reactions are the same. Any questions about that before we calculate delta G? Sorry. Yeah, so we're not actually done because this isn't even the core of our question, right? This is a part of our question. We need Ecell in order to calculate delta G, but this isn't delta G yet. So in order to calculate delta G, we'll use Faraday's constant. Does anyone know what that value is? So the value for F, or Faraday's constant, is what? F is equal to, if you can type it in the text box or shout it out, it's equal to, anyone? Yeah, there we go. So 96,485. And then the units of that is Coulomb per mole of electron. And we'll talk about units in a minute. We'll ignore the units for right now. But when we combine our Faraday's constant with the Ecell that we just calculated, the 0.646 volts, and then the number of electrons in our overall balance reaction. So when we add our reactions together, we see that we have 2 electrons in the products for oxidation and 2 electrons in our reactants for our reduction half reaction. So this is still, since they're on opposite sides of the reaction, this is a net process of 2 electron net process. So N is equal to 2. Faraday's constant is given. I already wrote it here. So this is our Faraday's constant. And we've calculated Ecell all the way down here. When we combine these 3 values together, we'll get delta G. And our delta G, or our final answer, should be equal to negative 1.2 times 10 to the 2 kilojoules. So this would be our final answer. That would be our delta G. And then since we're in standard conditions, this should actually be delta G standard, right? Any